Thank you very much. First of all, I'd like to thank all the people here coming to this conference, in particular from abroad, all the way to Japan in these difficult and complicated situations. Thank you very much. I also would like to thank the organizers, my students and my former students who have prepared this conference and made it possible in person conference. And in a way that is confidential to me, which is not visible to me. And so it's surprising, and I'd like to thank all of them. So it's a real honor to talk today. I did something new in early stages, but what I'm going to talk some further developments which have not been possible without my collaborators, to whom I'm grateful. So I plan to organize my talk divided it in three parts. The first, I'd like to address some very basic questions in representation theory. And then I'd like to ask some geometric questions. So this is a change of the topic on locally homogeneous space beyond the Riemannian setting. And then I'd like to talk about analytic questions on this new geometry. And the two will be partly new developments on these basic questions. So let me start with the first part, preliminary part. So some very basic questions in representation theory. First, we may ask if representation theory is useful or not in global analysis. This is a very vague question. So if geometry has a symmetry, we linearize it, then we have a representations on the function space. So this is the object for global analysis. And then vague questions is that if the group has a good control on the function space or not. So we need to make it rigorous and formulate. And then we recall some observation in representation theory. We can distinguish different irreducible representations, even if there exist continuously many inequivalent irreducible representations. But on the other hand, there's no way to distinguish isotypic representations if it shows up with multiplicities. So we may formulate these naive questions in terms by highlighting multiplicities, namely irreducible representations, how many times each irreducible representation occurs in function space. And it might be infinite. And then this means that we don't have a good control of the group on function space. Then for global analysis, we would need another approach. But if this has a finite or even better bounded or multiplicity free, then probably representation theory will be a powerful tool in global analysis. And so we want to understand when this multiplicity is controlled to have such questions. Then we recall some basic notions. Suppose X is a complex manifold acted holomorphically by complex reductive groups. And such a space is called spherical if a Borel subgroup has an open orbit in it. Examples include flag varieties and also complex reductive symmetric space spherical. And the work goes back to Aomoto and Joe Wolf, and then developed later by Matsuki. And also in the Riemannian case, there's a classical notion due to Selberg, weakly symmetric space, which is slightly more general than Riemannian symmetric space. And Akihisa-Wimberg proved that this Riemannian symmetric homogeneous space is weakly symmetric in the sense of Selberg if and only if its complexification is spherical. So this is an example. And so now we are back to this question. So this is the same slide as before, that we want to formulate these vague questions by highlighting multiplicities. And here is a theorem that interacts global analysis on geometry proved by Toshio Oshima with me. Namely, so for simplicity, we assume that G and H are pairable reductive groups. We may drop assumptions of reductiveness, but we shall use only reductive case today. Then the first condition is that the group has a good control on function space in the sense that multiplicity is uniformly bounded. So this is a property of representation theory and global analysis. And these conditions is equivalent to geometric conditions, namely the complexification is spherical. So in particular, this theorem includes a discovery that uniformly boundedness of the multiplicity in this space is detected only by the complexifications. And also, it is classically known that this condition complex geometry is equivalent to that. The ring of invariant differential operator is commutative, or also it is equivalent that it is polynomial ring. So we have the triangle that we are discussing about if representation theory is useful in global analysis. And this uniformly boundedness is particularly strong conditions than individual finiteness. And these conditions is characterized by the complexifications and complex geometry, and also by algebraic structures. All of them are equivalent. When we discovered this equivalence, we had a couple of proofs in mind. But we chose the following method in the paper. So namely, to prove the equivalence of geometric property and analytic properties, that we first capture irreducible representations as the solutions of system of partial differential equations. Then such a solutions may be captured by boundary values, so hyperfunction boundary values, if we have nice complexifications. And then things are reduced to the geometry of the boundaries. So this implies that if the geometry is nice, then we have a good control of function space. And the opposite directions is that if geometry is not so nice, then we don't have a control in the sense that the multiplicity may be infinite. For this, we construct intertwining operators, infinitely many linearly independent intertwining operators from the functions on boundaries. So it's generalizations of the Poisson transform. So this is a rough sketch, and it's not only equivalence of two conditions, geometric and analytic conditions, but also we get some estimate of the multiplicity by this method. Okay, so this is a topic about some basic questions on global analysis, but also we may regard it as an induced representation. And now we consider the real situations, namely branching problem. So this is a basic setting that we have a group and the group homomorphism and subgroups. So if we start from a group homomorphism from smaller group, and if this one extends to some G, then we may say this is a hidden symmetry. But usually this appears in opposite directions. If we are given a representation of the large group and then just related to G prime. So this corresponds to a broken symmetry. And the branching law is a description of this natural direction broken symmetry. And now we recall the philosophy of analysis and things, so classical philosophy of analysis that try to understand things in the following way. first, what is the smallest object? Then try to understand general objects like molecule, and then we want to decompose how they are built up from the smallest object, like molecules are built up from the atoms. And this consideration philosophy works very well for unitary representations. But if we consider non-compact subgroups on Hilbert space, then we have always irreducible decompositions, namely decomposed into the smallest object by means of the direct integral of unitary representations. But if G prime is non-compact, then such a decomposition may have a continuous spectrum and some discrete spectrum. So this is the usual situations. But occasionally, it has a very nice decomposition, so discretely decompose the restrictions. And so we ask another basic questions now about restrictions. So when some nice things happens for branching problem, restrictions. So we want to find an effective method to detect if there's this continuous spectrum or if this is discretely decomposable. And also, we also want to find an effective method to detect multiplicities, finiteness multiplicities. So the best situations would be these two things occur simultaneously. Namely, the restrictions does not contain continuous spectrum, namely discretely decomposable, and each piece appears with finite multiplicities. So this is, for example, true if G prime is maximal compact subgroup of Z. So this is a High-Chandler's admissibility theorem. But we are now thinking about non-compact situations. But if this conditions holds, that we call G prime admissible restrictions. Then we would expect detailed study of the branching problem, also by using purely algebraic approaches in these situations, if there's no continuous spectrum. And to give criterions, I recall some basic notions. Asymptotic cones. Asymptotic cones in a Euclidean space is that to look at the directions of the infinities. And this is definitions of the asymptotic formula in one formula. But it's better to look at the examples. If this is inside the parabola, asymptotic cone, infinite directions is here. And if it is inside the hyperbola, and then asymptotic cone is this closed cone. And asymptotic cone is always a closed cone. Okay, now back to representation theory. Fix a maximal compact subgroup and maximal torus, and then fix positive system. Then we define two closed cones. One is that given our representations, we consider all k types appearing in pi. So this is a countable set. Then take an asymptotic cone. So this is called asymptotic k support. So this is a closed cone defined by representations. We also define another closed cone, now defined by subgroups. So this is a pair of subgroups, reductive groups. Correspondingly, we consider maximal compact subgroups. Then we consider Hamiltonian actions on this cotangent bundle and take a momentum image. Then we have a closed cone. Now, this is a theorem that when we have a discrete decomposabilities, the answer is the following, that if two closed cones, one is defined by subgroup and the other is defined by representations has a trivial intersections, then first, the restrictions to this small compact subgroups has finite multiplicity, k prime admissible. And actually, this is necessary and sufficient conditions. And then in this case, the restrictions is G prime admissible, namely G prime is non-compact, but the decomposed without continuous spectra, and each multiplicity is finite. A very special case where G prime equals Z, then the closed cone defined by subgroup is trivial. So in this case, the conclusions is High-Chandler's admissibility theorem. So to understand this property, so this is a property of the triple, namely the group, representations, and subgroups. And then when we are discussing when there's no continuous spectrum and finite multiplicities. So in some sense, this Hilbert space should be small relatively to subgroups, or subgroup should be large relative to the Hilbert space. But to make this rigorous, we use the following ideas that capture the singularities of hyperfunction characters by means of its holomorphic extensions in complex domain. And then this estimates the size of a complex domain with respect to the subgroups. This is an idea of the proof. And then later, I also gave some different proof by using a more algebraic proofs, abelianizations, and some symplectic geometry. Okay, and let me give some examples. And so we recall the Bernstein correspondence between irreducible High-Chandler modules and KC equivalent D modules on the complex Frag varieties. And then we can associate a single closed KC orbit on the Frag variety such that its closure is the support of the corresponding localizations. And in the case G equal U22, and then complexifications is this one. And then there are 21 orbits. One is open orbit and 6 closed orbit. And then let us consider irreducible representations that have the same infinity character with the trivial representations. Then there are correspondingly 6 discrete representations. And most of them are unitarizable and actually can be written by means of Zuckerman's Dirac functor modules. 18 of them can be written by means of Zuckerman's Dirac functor modules. And they are unitarizable. And some of them in the red color are unitary highest-order modules. And this intersection corresponds to the highest holomorphic discrete representations or anti-holomorphic discrete representations. The Gelfand-Kirchhoff dimension in this case is 4. Then there are some other discrete series representations of Gelfand-Kirchhoff dimension 6 and Gelfand-Kirchhoff dimension 5. So this is some introduction of these representations. Now we want to restrict such representations to non-compact subgroups. So let us restrict to subgroup of U22. Inside there's a spin for 1 inside here, or isomorphic to SP11 by using quaternic number. Then the green color is actually admissible, namely there's no continuous spectrum and with finite multiplicities. And the other ones has a continuous spectrum. And this is a kind of a classification theorem. And then further classification results are developed by Vargas, Yoshiki, and Di Vargas, and others. Okay, and actually the first discovery for me is that I try to restrict discrete representation of Gelfand-Kirchhoff dimension 5 to this subgroup SP11 or spin41. And then obtain the following multiplicity-free and discrete decomposable formulas. So namely, this representation is High-Chandler's discrete representations. So usually there are 4 parameters, but for simplicity, I just put 2 parameters. And then this part is discrete representations for the subgroups, spin for 1. And then this is multiplicity-free decompositions. I'll explain some geometric background of this formula. But before that, I would also like to mention that so various directions of generalizations of this one. So like abstract theorem for discrete decomposabilities that we saw in theorem B, but also this multiplicity freeness can be generalized like multiplicity bound theorem, like theorem A and its variants, and also recently developed by Kitagawa and others. And also more strongly that we may focus on multiplicity 1 properties like theorem by visible actions and by also Sun and Zhu by another method. And also This one is locally isomorphic to this one and also related to the gross cluster conjectures. And also explicit branching laws has been developed by these people and also many other people. So there are many directions for generalizations, but this is a kind of simplest examples. And actually that this example I discovered when I was studying by some geometric questions that I was looking at three-dimensional complex manifold, indefinite Kähler manifold, which is a non-convex domain in P3C, on which U22 acts holomorphically and isometrically with respect to this indefinite Kähler structures. Then we have a regular representations. Then the Laplacians, so this is a real dimension 6, so the Laplacian is of this signatures. And then we have a L2 eigenfunction spaces on which the whole group acts as irreducible representations. So this is a discrete representations in the sense of French-Sensen, Oshima-Matsuki. And then I was curious to decompose this into this subgroup, because we shall see that this group acts on this space properly. And the proper actions is a kind of very nice non-compact actions. And so I was curious how this proper actions is reflected in function space. And then found that there's no continuous vector. And so I'm more general that I'm talking about the branching problem. But this representation is appearing in some global analysis. And then to understand global analysis, we may recall the previous triangle. But now, additionally, we have another data subgroups. Then the algebras, we have a larger algebra because G prime is smaller. So this invariant differential operator is larger. And so by using these structures, we may think of this branching problem. And this is a theorem. And this is proved by much later in this generality with Fanny that we consider a triple of real reductive groups. And suppose that this one is reductive symmetric space, and this subgroup G prime acts properly, and also complexifications act spherically. Then the theorem is the following. For any irreducible representations of the large group G with non-trivial H distinguished vectors, namely, there's a non-trivial H fixed vector in the distribution vectors. Then restrict to another subgroup G prime. Then this restriction does not have continuous vector, and multiplicity is uniformly bounded. So this is a theorem. And we also have some stronger theorem, but today it is enough with this theorem. So this is some basic questions related to representation theory and also global analysis. And then we have given some answers to these questions. Now let me change topic, that some geometric questions on locally homogeneous spaces. So symbolically, I write this geometry as a new music instrument beyond the Riemannian geometry. And I want to construct a nice instrument, handy one, like compact ones or finite volume ones. And also to make it music instrument, we also need some deformation theory, like longer strings or shorter strings to have more sounds. So we also want to discuss constructions of some compact manifold with some nice geometric structures and also possible deformations. And then later we want to try to hear this sound. So this is what I'm going to talk about the latter half. Okay, now let us start with this part. So the first thing that we have to observe is the difference between Riemannian geometry, classical Riemannian geometry, and indefinite metric, new setting that we are considering. Namely, in the classical situations in the Riemannian manifold, we consider discrete group consisting of isometries, and then identify its orbit. And then quotient space is automatically Hausdorff space. If we consider the same things for indefinite metric, and then quotient space is not necessarily Hausdorff. What is the difference? So difference is that we need to understand difference that property of the group itself, namely discrete group of isometry. So this is a property of the group. And the second one is property of the actions, namely gamma acts properly discontinuously, for which we call discontinuous group for X. So this is a property of actions. Then in the Riemannian case, this is the same notions. But in the non-Riemannian case, this is not the same notions. And the difference is that proper actions. And so I wanted to understand, to find effective method to detect proper actions as a first step of this problem. So the third basic problem that I try to attack is the following. Try to find effective method to detect when some group acts properly on manifold. And so the actions, proper actions is that the action map is a proper map. And we consider the following setting. G and H are pair of reductive groups. And then by using a Killing form, this quotient space has naturally indefinite metric on which the whole group G acts isometries. But these actions cannot be proper unless H is compact. But if we take some smaller subgroups, then we may have proper actions. And so we want to detect conditions of the triple of the group for which G prime acts properly on Z mod H. And in the case, all the triple of the groups are real reductive groups, we have a very simple answer as follows. Namely, these topological conditions, properness conditions on the triple of the groups, triple of reductive groups, is equivalent to some linear algebra conditions. What is this linear algebra conditions? This is inside A, which is a maximum split abelian subspace in the Lie algebra. Similar subspace can be considered for each group that I denote by AH or AG prime. But this subspace is not contained in A in general. But after taking inner automorphism, we may bring this subspace into a subspace for A, which I denote by AH or A round Z prime. And these spaces are unique up to the little wide group for restricted root system. And so this theorem says that these topological conditions, properness conditions for the triple can be detected by linear algebra conditions. And this can be very easily checked. So this is a necessary and sufficient condition. And by using this, we may construct some nice instrument, nice geometry as follows. First, we consider pair of real reductive groups. Then we have assured Riemannian manifold on which the whole group acts isometry. But this action is not very good, so it's not the proper actions. And by using the criterions, we can find reductive subgroups as large as possible which act properly. And this we consider as a kind of safety zone. And inside this safety zone, anything can act properly. And so in particular, if we take torsion-free discrete subgroups, then this acts properly discontinuously, freely, and isometrically, so that the quotient carries all local geometric structures, original local geometric structures, and the quotient space is Hausdorff and smooth manifold. And we call the resulting manifold is a standard quotient. And by using this method, sometimes we can find a very large subgroup Z prime and then taking a compact lattice, finite volume lattice, that we have a nice quotient, handy ones. And so we can construct for several families of homogeneous space. And also there are some isolated, sporadic ones which has a compact quotient. So we can find such a families. And some of the isolated families, sporadic families that we gave some uniform treatment with Yoshino. And then recently Tojo gave some theorem for exhaustions that what we have found exhausts all the cases under certain natural assumptions. Okay, so this is construction part. And also there are a lot of interesting stories about the abstractions, but today I only look at the positive results, so existence part, to make some new music instrument. And one more thing that terminology that we call standard quotient. This means that there also should exist non-standard one. Yes, that it may well happen that a discrete subgroup acts properly discontinuously, but its Zariski closures does not act properly on X. This happens. In such a case, the quotient is not standard, for example. And to treat also for non-standard case, that we need to generalize criterion, properness criterions. And this was done by Yves Bunor and by myself, the properness criterions. So I write in the following way that this is the reductive groups and the closed subgroups and discrete subgroups. And we consider Cartan projections with respect to KAK, or its projections to dominant wire chambers. Then the following two conditions are equivalent. One is the topological conditions, namely these actions of discrete group on Z mod H is properly discontinuous. So this is the conditions of the triple. So this is the topological condition. And the second conditions is again in the same vector space. And this is the Cartan projections of H, and this is the Cartan projection of gamma. And this epsilon denotes the epsilon neighborhood. And the intersection of the epsilon neighborhood of this is relatively compact, so it's a bounded set. So this is the equivalent conditions. So this generalizes the properness conditions when I explained for the triple of reductive Lie groups. But now here gamma is discrete subgroups. Okay, so we are now here, and in particular now we are going to talk about a little bit about deformations. Okay, now what is deformations of quotient? To deform it, we need to fix something and then deform something else. So we fix geometry and the transformation group Z. And also we fix discrete subgroup gamma of Z. And then try to deform this homomorphism. So this very injective in homomorphism phi. Then we are tempted to say that X modulo gamma through phi is varying, is the deformations of X mod gamma. We want to say this way. But then there's, of course, problem that one is that if there exists a non-trivial deformations of phi or not, of course, we may rotate by inner automorphism, but we are interested in non-trivial deformations, not by given by automorphism. So we want to find the non-trivial ones. And even if we have non-trivial deformations, but the small deformations may destroy topological property like properly discontinuous actions. Here's a very elementary examples that small deformations destroys proper discontinuous actions. So we consider abelian setting. So Z abelian group acting on real line generated by X going to one step X plus 1. Then we may think of deformations. One is the deformations of this part, and the other is deformation of this part by small epsilon. The first deformations just change the radius, and the topology is the same. But on the other hand, the second deformations, then the quotient space, the topology is different for any epsilon which is non-zero. And this is a non-Hausdorff space. And so actually that the actions generated by these actions for non-zero epsilon, proper action is destroyed. So this means that proper discontinuous actions may be destroyed under small deformations of the actions, but sometimes it is preserved. There's another example that posed by Bill Goldman. Consider PSL2R. By the Killing form, it carries some Lorentzian manifold structures such that the constant curvature is negatively constant. So this is the anti-de Sitter space. And simultaneously, this has the group structures. So we take co-compact discrete groups and just take a quotient by left actions. Then we get a three-dimensional compact anti-de Sitter manifold. So all the local geometric structure is preserved. Then we think of the deformation of this by considering a graph of gamma in the following way. Take a homomorphism rho and then form a graph of gamma. This is a group inside the direct product group, which is abstract group. It is isomorphic to gamma, but it is a deformation inside the gamma, g times g. If rho is trivial, then this is the left actions. Then Goldman raised the following conjecture, that if rho is sufficiently close to 1, then gamma rho, namely the left actions, which is now deformed from the left and right actions simultaneously, still preserves properly discontinuous actions on this anti-de Sitter space. So he is talking about different phenomena, not this side, but this side. So this is his conjecture. And then we may formulate the following, that if these, we consider again triple of reductive groups, and then assume that G prime acts G mod H properly. This can be detected easily by the criterion that we have seen, theorem D. And then take a co-compact discrete subgroups. Then we deform gamma as far as it keeps group structure in an obvious way, namely consider homomorphism into the centralizers of G prime and H. Then we consider such a deformations. Then what we can prove is that this proper discontinuous actions is preserved under small deformations in this sense. So in particular, if H is trivial and G prime equals Z equals PSL2R, this implies that Goldman's conjecture is true. So this is a primitive theorem. Now there are much developments have been made in the last 20 years. Nilpotent Astrobal case by Nasrin, and also Baclotti and his collaborators, and Yoshino, and for reductive case by Kassel and her collaborators, and also recent work by Kannakas are working on deformations, much more general case. And let me give a small idea of the proof. So for this, we recall two elementary geometry. One is an asymptoticon that we first saw at the very beginning of the talk, and also we consider epsilon neighborhood. So I illustrate by examples. And for discrete decomposability of the unit representation, we use this. And for proper actions, we use these ones. But now we consider, so this is properness criterions that we have explained D prime, that by using epsilon neighborhood of the Cartan projections, this topological conditions is equivalent by using epsilon neighborhood. But instead, if you use an asymptotic cone, then this gives a stronger conditions. That in a joint paper with Fanny that we named this action sharp. So this is a strong proper discontinuity. And actually we introduced some quantitative constants, sharpness constant, to measure how strong proper discontinuity holds. And the point of the proof of theorem E is that sharpness conditions tend to be more stable under small deformations. And then if we start from sharpness and then this condition is stable under the previous setting. So this is a connections of this one. Okay, so now we have explained some geometric part. Of course, there are also interesting things, as I mentioned, that some obstructions and also sometimes we don't have deformations. And then in such a case, rigidity, but today I'm not going to talk about it. But now let us hear the sound of this music instrument. So we have now some new geometry beyond the Riemannian setting, then we want to hear its sound. Then first, we need to begin a formulation. So to formulation spectral analysis on this one, we recall our previous notation. This is a ring of invariant differential operators on homogeneous space. And suppose that the gamma acts properly discontinuous and freely, so that the quotient space is a Hausdorff manifold, and this is a covering. Then any invariant, G-invariant local geometric structures can be pushed toward to this space. Also, differential operator is a local structure, and so we can push forward any invariant differential operators to this space, to which we refer as intrinsic differential operators on X among the gamma. So intrinsic differential operators include, for example, Laplace-Bertrand operator. If this is a isometric covering, then we have a Laplacian here and Laplacian here, and this push forward is a typical example of this one. Then what is the general questions that we have in mind is that try to understand Jorgen eigenvalues of these intrinsic differential operators. And also, this F is the joint eigenfunctions. We want to understand such a joint eigenfunctions and also eigenvalues. Where we are considering joint eigenvalues, so this lambda is not a number, but formulated as an algebra homomorphism. And then second question is that we want to develop arbitrary functions on this quotient space into eigenfunctions. So this is the general question. Of course, this is a very difficult question, even in a very special setting. Like gamma is trivial group. So gamma is a discrete group, but even if gamma is trivial, even if H is compact, even if G is abelian, this general questions has been developed deeply and in a rich way for long history. For example, when gamma equals E, in particular when Z mod H is a group manifold or semi-simple Riemannian symmetric space or semi-symmetric space, that there's deep theories by Oshima and Matsuki and others, Sekiguchi have developed a lot. And also recently, real forms of spherical manifold is developing. And on the other hand, if H is compact and gamma is arithmetic, and in such a case, this question is closely related to the automorphic form theory. And also, again, there's a lot of important deep works and developing. But even when Z is abelian and H is trivial and gamma is lattice, the understanding the distributions of just eigenvalues is very difficult questions for the indefinite metric. For example, including Oppenheim conjecture, which first attacked by analytic number theory for many years, and then later solved by different method, by dynamical method by Dani and Margulis. So even in the abelian case, this contains a very deep problem. But still, we want to challenge even new situations where G is non-abelian and gamma is non-trivial and H is non-compact. Then further difficulties, of course, will arise. And the geometric new difficulties that we have already seen that if there's a nice geometry or not, and so sometimes we don't have obstructions to have a compact volume, a compact quotient. And sometimes we have a rigidity theorem. But also we have some nice geometry, compact quotient, a finite volume quotient, and some of them allow some non-trivial deformations. So, so this is related to the local to global geometry, namely, if we fix local homogeneous structure, and then how global nature of the manifold. And this is very difficult beyond the Riemannian setting. But this is also connected with such a geometry. And we looked a little bit about flavor of this. And then for analytic problem, if we can expand the functions, then there must be some operators must be self-adjoint extensions. But if it is not a Riemannian setting, then it's not clear that Laplacians, which is not the elliptic one, has an essentially self-adjoint or not. So it's already not clear about this point. And also for representative theoretic part, that if H is non-compact and the gamma acts properly discontinuously, then always the volume of the mod gamma is infinite. So this means that we don't have a good control on function space by the group, as we discussed at the very beginning of this talk. And so this regular representation, function space on Z mod gamma is not well under control by representation theory immediately. So this is another difficulties. So we need to bring some new ideas. Some of them are geometric ideas, like counting orbits in the Schur-Riemannian manifold that we worked with Fanny. Today I'm not going to talk. But also we bring some new machinery, which I have explained in theorem A and theorem C at the very beginning. So this will give us some new machinery to attack, to challenge this spectral analysis, as we shall see. Now let us look at more precisely. The first setting is a very special setting for symmetric space, but important setting. Namely, Z mod H is a reductive symmetric space satisfying the rank conditions. So in this case, this symmetric space admits discrete representations. The sufficiency of this rank condition was proved by French-Jensen, and the necessity of this rank conditions was proved by Hoshima and Matsuki. So now it's a necessary and sufficient conditions. Under these conditions, we prove the following theorem with Fanny. For any sharp discontinuous group, namely strong properly discontinuous actions, then there exist infinitely many L2 eigenvalues on the quotient for intrinsic differential operators. For this gamma, we don't assume any assumptions. So we allow gamma is trivial, and then we back to these stations. And also, we don't assume X mod gamma is of finite volume, so it allows infinite volume. But still, there exist infinitely many L2 joint eigenvalues. And moreover, some stabilities of the spectrum under deformations. For example, if we assume standard quotient, in the sense that a simple subgroup, simple Lie groups of real rank 1 acting properly on Z mod H, we can detect these conditions by criterions, and then take a compact lattice. Then infinitely many L2 eigenvalues on this quotient remain stable under small deformations of gamma. So small deformation of gamma in this case preserves proper discontinuity, so preserves nice topology, but also preserves nice spectral properties that these L2 space, infinitely many of them are stable under deformations. So for this, we need some uniform estimate in geometry and also analytic properties. And in particular, this is in contrast to the classical Riemannian setting. For example, for the compact Riemann surface, that the eigenvalues of the Laplacians on compact Riemann surface vary if we regard it as a function of Teichmüller space. But in fact, the proof of the previous theorem includes the following theorem. That we consider any three-dimensional compact anti-De Sitter manifold. Then the hyperbolic Laplacians, this is a Lorentzian manifold, hyperbolic Laplacians has countably many L2 eigenvalues of this form, where n is any even integers larger than some constant depending only on m. And this is stable as functions of higher Teichmüller space locally. So this means that, so symbolically, that if we consider musical instrument in Euclidean space in here, that we have longer strings, shorter strings, and then the pitch becomes higher if the strings are shorter or strings are thinner, then we have a higher pitch. And so sound changes. But in the not the Riemannian space, but in the Lorentzian space in this case, there are infinitely many sounds which do not change even if the, we change the deformations. So there are some intrinsic sound of this instrument. So this is somehow what this corollary says. And another corollary of the proof of this theorem applies to the classical setting that we consider just Z mod gamma, and then we have a left quotient. Then we have a regular representation of Z on L2 Z mod gammas in this setting. So this is that we regard a group manifold. And then now we assume the rank conditions. And then take any, for simplicity, torsion-free discrete subgroups. Then the proof of our theorem says that all discrete representations in the High-Chandler sense with sufficiently regular parameters appears in this L2 Z mod gamma. Here we don't assume gamma to be of finite volume. And so even if it is an infinite volume, still all discrete representations appear for sufficiently regular lambdas. And much earlier there are works for, in particular, when gamma is a lattice, like Kajdan, Jansuli, De George Wallach, Klose, Ross-Spey, and they treated the arithmetic subgroups. And usually they consider sometimes replace gamma by congruous subgroups gamma prime deep enough one, possibly depending on lambdas. But proof shows that we can take independence of lambdas in corollary. And this independence of lambdas will be also used later in our the last theorem about the multiplicity of spectrum. Okay, but this is some special sound that we call universal spectrum, corresponding to averaging of discrete representations of Fred-Stevenson and Oshima-Matsuki. But now we want to consider more general case where Z mod H does not have a discrete representations, so does not satisfy rank conditions. And so still we want to capture all sounds, not necessarily discrete sounds, but also continuous spectrum. So how to capture all sounds? So we limit ourselves to the standard case. Namely, the standard case we recall the following setting. So we consider usual setting and then take a safety zone. So this is a subgroup acting properly. and we know computable criterion here. And inside it, it's a safety zone, so any discrete groups, for example, torsion-free one, act properly discontinuously and freely, and we get them Hausdorff manifold. So this was a standard quotient. So this is our setting. And also this is already we have explained that we are looking at joint eigenfunctions of intrinsic differential operators, like non-elliptic Laplacians. But usually we also have other intrinsic differential operators other than Laplacians. Some of them are algebraically independent differential operators. And we want to consider simultaneous eigenfunctions. And then want to develop such ones for arbitrary functions. And here's an expansion theorem. So this is the previous theorem. The key assumptions of this theorem is the following. Assume that complexifications, so G prime acts properly. This is a general assumptions. But in addition that complexifications act spherical. Actually, we have classifications when this happens. And then there exists a measure on the set of the parameters, spectral parameters, and the family of the kind of Fourier transform maps from the arbitrary functions of complex supported functions to the joint eigenfunctions, such that any compactly nice function compactly supported functions can be expanded into joint eigenfunctions of intrinsic differential operators with L2 correspondence. So this is prepared with Fanny-Kase. So this theorem includes, in particular, that in the same assumption that the Laplace-Bertrand operators has a unique self-adjoint extensions, namely essentially self-adjoint. And so this is why we have such an expansion theorem. Without self-adjointness, we don't expect such an expansion theorem. And moreover, in our setting that G mod H does not have does not necessarily satisfy the rank assumptions, and so G mod H does not admit discrete representations. But for the quotient, like a co-compact quotient, then we may, in this case, in this station, that no continuous spectrum appears, and infinitely many L2 eigenvalues of Laplacians appears in this spectral analysis. This is corollary. And roughly speaking, the situation is the following for the strategy, the proof. I don't go into details, but just to give some flavor. The first one is geometry that we have already seen. That if we have a safety zone, and then inside here, we have a nice geometric actions, and then nice geometry. This we symbolically we say music instrument. Then we are trying to hear the sounds. And then we want to develop joint eigenfunctions of these intrinsic differential operators. We also can consider not only x, but also x mod gamma in this diagram. Then, in general, this larger algebra cannot act on this space. But if GC prime acts on XC spherically, as we saw in the first part of the talk, that if representation theory is useful or not, then we encounter these conditions. And if this condition is satisfied, then this larger subalgebra stabilizes this subspace. So this is considered as a hidden symmetry of the algebras. And then by using this, we use branching law. So this space is responsible by the irreducible representation of the larger group. But then to look at the finer structures, we decompose it in G prime. Then this topological assumption properness somehow implies that this irreducible representations realized in the distribution space is admissible. Namely, there's no continuous spectrum and restrictions to be discretely composable. I should note that in the representation side, there's no continuous spectrum. But in this theorem, there may exist continuous spectrum. But this is a rough idea of the proof. And so more precisely, we use the last part is that we use a branching problem, then which are realized on the distribution space on this one. So this is a global analysis problem. But now we want to understand this global analysis together with the subgroup Z prime. Then this larger subalgebra is respond to the representation of subgroups. And so if we want to understand the difference of these subalgebra, we would understand better on these ones. And then to understand this, we use now this triangle geometry. And there's some canonical fibrations as actions of the subgroups. So like a kind of a hop fibrations. And then by using these fibrations, there's some fibers, and this fiber is responsible another subalgebras. And this subalgebras actually controls the branching laws. And then all these triangles helps the proof of the theorem, part of the theorem, expansion theorem. And so in the first example that we saw, branching of U22 to SP11 also relates to this geometry. Namely, this representations is Hessian discrete representations, but also simultaneously discrete representations in the sense of Fuller-Sensei Oshima-Matsuki for this simple symmetric space. And then in this case, we use such a geometry, and this is actually the proof of these formulas, and also proof of the spectral decompositions of arbitrary functions on locally symmetric space. And we have seen that if these representations contribute spectrum, and then also each of the pieces contributes the spectrum. And so this also gives some infinite multiplicity theorem that I just mentioned. This is in preparations with Fanny Castle, a paper, analyticity of punctuations, that there exists, for some spectrum, the multiplicity is infinite. For what we call the universal spectrum appears with infinite multiplicity. And I think time is up, so I think we should stop. And so there are some work joined with Bernstein for non-standard, some new phenomena for non-standard cases, but I hope to talk in another occasions. But just a summary of what I have talked today is that we asked a very naive and basic elementary questions in representation theory. If representation theory is useful for global analysis, and then met notions of real form of spherical space, and also branching problem, existence of continuous spectrum and finiteness of multiplicity. So this was theorem B and C. And then we have discussed some constructing some new music instrument beyond the Riemannian geometry. Then the key point is to understand the proper actions. Then we give some criterions for proper actions. Then also encounters sharp properness actions. And then discuss some deformations of this one. Then finally, we try to listen this new music instrument. And then somehow this machinery, also there are some other machinery that I didn't mention about geometric method, all together are used to hear this sound. So I think this is a good place to talk. So thank you very much for your attention.